Okay, so I am off getting vaccinated today. So I wanted to do basically an asynchronous video for you so that those of you in B and C blocks will still get a chance to at least hear my voice and go over the notes. Now, there's a worksheet that is associated with today's lecture notes. The pressure volume worksheet or Boyle's Law worksheet, whatever you'd like to call it. It's due Thursday, just so you know. So it won't be due tomorrow. You'll have a chance to actually, if you want to come to between 10 and 12 to get help, you'll have a chance then to do it. Now, it's the second class. Now, we already talked about pressure and how to measure pressure in units and how to convert between them. But now I want to start applying things. We talked about the factors that affect gases: pressure, volume, temperature, and moles. And there's a bunch of relationships that scientists were able to work out when they looked at the relationship of two of the variables when the other two were held constant. And we're going to talk about those laws. The very first one was called Boyle's Law, and it's what happens if you have temperature and moles constant and you vary pressure and volume. So I want you to think about it. What happens to a balloon if the pressure outside the balloon decreases? What would you expect to happen to the balloon? Well, the balloon will get bigger. And let me show you, this can be demonstrated using a bell jar and a vacuum pump that can reduce the pressure that surrounds a balloon or anything else for that matter. So let's take a quick look at the video.
Hi, I'm John from Edwards Vacuum, here in the Global Technology Centre in the UK. I will be demonstrating Boyle's gas law using a vacuum pump, which will draw the air out of our bell jar, and a balloon. Boyle's gas law describes an inverse relationship between pressure and volume. So, let's take a look. We'll place our balloon in the center. And now we'll open the valve on the vacuum pump side to let it draw the air out. What we see occurring now is, as pressure is dropping, the volume of the gas inside the balloon is increasing. The next step is we can let the air rush back into the bell jar, and as pressure increases, the volume should decrease. A good tip is to let air in slowly, as the balloon may pop. As the air is rushing in, you can see that the pressure around the balloon increases and the volume of the gas inside the balloon decreases. So now we have demonstrated Boyle's gas law. If this experiment is repeated, please have an adult present. Thank you.
Okay, so I think you get a pretty good idea from that what happens, right, when we change the pressure outside a balloon. Remember what pressure is caused by. It's caused by the movement of particles hitting a surface, and it is dependent on the temperature and the number of particles. So normally the balloon just sits there without any apparent change in size because the particles of the air hitting the outside of the balloon are basically balanced by the particles inside the balloon hitting the inside of the balloon surface, and so the balloon doesn't change in size. When you put it in a vacuum, fewer particles are hitting the outside of the balloon. You still have the same number of particles hitting the inside, so there's a relative pressure difference, and so the balloon will expand until the number of particles inside and outside are hitting at the same amount of force, so that the balloon will no longer change size once it expands enough. Okay, so let me just remind you the four variables that affect gases. Okay, volume is one of the things that we're going to be looking at. So in all the various gas laws, that's one of the variables, or it may be something we hold constant. Pressure is another one of the variables and or something we hold constant. Today we're going to be talking about Boyle's Law, which is where volume and pressure are allowed to vary, but moles and temperature are held constant. So the temperature stays constant. Remember, we're always going to deal with temperature in Kelvin in any gas law equation. And the moles of the gas are going to be held constant. So if you're talking about a balloon, the amount of gas, the number of particles or moles of gas, atoms and molecules inside the balloon doesn't change. All right, it's a sealed container. It's a flexible sealed container. Okay, now, key assumptions. Boyle's law is the relationship between pressure and volume, and it's when This is only true when the temperature and moles of the gas are held constant. So this is the way the equation is written for Boyle's law. The initial pressure and the initial volume will always equal the product of the second pressure and the second volume. So units of pressure for this equation have to be the same on both sides. If they're not the same on both sides, we won't have a valid relationship. And the units of volume must be the same on both sides. So if you have milliliters as your second volume and liters as your first volume, then you're going to have to convert them to be either both milliliters or both liters. If your pressures aren't the same, say it's atmospheres on one side and kilopascals on the other, you're going to have to make sure that when you're solving this equation, that you solve for one, adjust your units so the units are the same on both sides as well. And we'll go through examples of how to do this. Now, if we were to graph this, let's think about this. How does this work? Well, for one thing, I just said that Boyle's law, the pressure, initial pressure and final pressure will always equal the initial volume and the initial pressure will always equal the product of the final volume and the final pressure. Here's some examples of data that you could collect. Take a look. What if you multiply the volume by the pressure in each case? Do you notice that they all become one? They're all equal to each other because if you have, for instance, a 1 atmosphere pressure and a 1 liter balloon, and you were to have the pressure, the volume doubles. If you were to quarter the pressure, the volume goes up by a factor of 4. Similarly, if you started with a 1 liter balloon at 1 atmosphere, if you double the pressure, it gets smaller by half. If you make the pressure 4 times more, it gets smaller by a factor of 4. Now, if we were to graph this, you're going to see what kind of relationship it is. It is an inverse relationship. When pressure goes up, volume goes down. Pressure goes down, volume goes up. So they go in opposite directions. And if we were to graph this as a function of volume and pressure, take a look at what we get. Do you notice that as the pressure goes up, the volume goes down? As the pressure goes down, the volume goes up. This is a standard graph. It's a hyperbolic graph. In theory, although in practical you can't do this, if you could reduce the pressure infinitely, you would still never, in theory, hit the volume axis. You would just go to infinity. But for any practical standpoint, like the kind of data that I showed you in the graph, in the table before, you'll see that you'll get this kind of shape. It'll approach the axis, but it won't get there. But we can't go to far enough extremes to see if anything else would happen. Now, how do we solve Boyle's law problems? Okay, so here is a simple problem. What is the final pressure in atmospheres if 0.0532 liters of gas in a sealed container at 1.02 atmospheres of pressure is expanded to 1 liter at constant temperature? Now listen, here's the key things. Temperature doesn't change. It's a sealed container. That tells you that the number of particles, the moles of gas, doesn't change. So Boyle's law is a valid representation of the relationship between volume and pressure in this case. So how do we do this? Let's figure out what our initial and final volumes are and what we're solving for. We're looking for the final pressure. So we're looking for P2. So we do know the second volume here. This one's our initial volume. This is our initial pressure. This is our final volume. All right, so let's set it up. One of the things, yes, we can use it because moles are constant, temperature is constant. So Boyle's law works. So here are how I'm assigning the variables. The initial volume is 0.0532 liters. The initial pressure, 1.02 atmospheres. We know what our final volume is. We're told that. And we're trying to calculate the final pressure. So we plug it in, solving for P2. Now, remember it was P1 V1 equals P2 V2. So we're solving for P2. So we're going to end up with P1 times V1, and it will be divided by V2. And when we go through and do that, here is our final pressure, 0.0543 atmospheres. Why do we have 3 sig figs? This has 3, this has 3, this has 4. In the end, the term that has the fewest is 3. So we're going to be rounding it down to 3 atmospheres. Now, here's a slightly more complicated example. All right, so we've got a balloon that's 50.45 cubic centimeters of gas. It's at 560 torr, that's the pressure. And it says at the surface of a uniformly heated pool, it is then submerged to a depth of 10 feet. Now, listen to me, guys, all right? Uniformly heated means the temperature is constant, okay? It is a balloon, it's a sealed container. Moles are constant. The depth of 10 feet is a distractor. It has absolutely nothing to do with solving the problem. They're just telling you where the balloon went. Now, when the balloon is submerged, the pressure is now 346.73 kilopascals. Now listen to me. We got cubic centimeters, we've got torr, we've got kilopascal, and now we're being asked for the volume of the balloon in liters. We're going to have to do some unit conversions here to solve this, okay? We need to get the pressures to be the same. Doesn't matter whether we go to torr or we go to kilopascal, but we got to have the pressures the same. Secondly, we've got to have the volumes of the same units. Again, it doesn't matter if we go to cubic centimeters. Well, actually, it kind of does. It says, what is the volume of the balloon in liters? So what we want to do is convert this to liters so that we'll get our final volume in liters. Can we use Boyle's law? Yes, because moles are constant, sealed container, temperature is constant, uniformly heated pool. Okay, so what do we got to do? I'm just going to first assign all the variables. Here's our initial volume. Here's our initial pressure. Here's our final pressure. Here is our what we're trying to find, which is our final volume. Got to do some unit conversions. Okay, got to convert. So let's convert cubic centimeters to liters because we know that our answer has to be in liters and we need our units to match. So what we do is we take our 50.45 cubic centimeters and divide by 1,000, and now we will have it in liters. We still have 4 sig figs, didn't go anywhere. Now we got to convert the pressure. Again, it doesn't matter whether you convert kPa to torr or torr to kPa. You're going to get the same answer, okay? So we're just going to pick one. We're going to pick converting torr to kilopascals. Again, we go back and look at our sheet that's got all the unit conversions. For every well, this is actually more complicated than it needs to be. First, what I did is I converted to atmospheres, and then I converted atmospheres to kilopascals. You can actually go directly to kilopascals if you go back and look at your unit conversion sheet, okay? But basically what we're doing is we're going from 560 torr to 74.6 kilopascals is our actual pressure, all right? That's what this 560 torr is, okay? So we know our initial pressure, we've converted our initial volume to liters, and we know our final pressure in kilopascals. So now let's move over here and figure out how to solve this and come up with our final volume, okay? So there's our equation, P1V1 equals P2V2. We're solving for V2. So P1 and V1 will be divided by the second pressure. Here is our initial volume. Here is our initial pressure. Here is our final pressure, and we're trying to find X liters. So when we take this product, divide it by 346.73, our final volume is 0.0109 liters. Now, I also want you to think about this from a standpoint of common sense, okay? Once we know what the pressures are, we'll see that the initial pressure is a lot smaller than the final pressure. So our volume had better get smaller. If our volume doesn't get smaller, there's no logic to this because when the pressure goes up, more force is pushing on the outside of the balloon. And so the balloon's going to have to shrink so that eventually you'll get more particles hitting per unit area to restore the sort of equilibrium. And then the balloon won't change in size anymore, change in volume anymore. So the final volume should be smaller. And indeed it is. This is 0.05 liters roughly. This is 0.01 liters, so it went down by almost a factor of 5. Now, what do you need to do? Okay, that's it for the notes. What do you want to do if you haven't downloaded the worksheet? You want to go here, click on Boyle's Law worksheet, okay? There's always like I've been like putting this on the top. This is just a handy set of conversions and units that you might or might not need to use. And it's got a bunch of formulas, okay, which you may or may not need to use. Right now, the only formula you need to use is P1V1 equals P2V2, because that's all we're doing today, is working on Boyle's law. This is Boyle's law. You have 6 questions, okay? So you want to go through and do these. Remember, there could be data, numbers stuck into the sentences. You got to be able to read the sentences that have nothing to do with the problem. Just identify your P1s, V1s, P2s, and V2s. You're going to get 3 of them, and then you're going to solve for the 4th, whatever the 4th one is. All right, so that's all we're doing today. You spend the rest of your time, please, working on the worksheet. The worksheet is due Thursday at the beginning of class. Okay?